Hello, dear friends. This is Dr. Pankaj Nagpure, Associate Professor, Department of Physics, Sri Shivaji Science College, Amravati. In this lecture, I will discuss the principle of Raman effect and how it can be used in Raman spectroscopy to perform qualitative or quantitative analysis of a given sample. Let us first understand the Raman effect. Let a sample is exposed to the monochromatic light in visible region. The sample absorbs light and most of the light get transmitted through the sample. However, a very small part of the light is scattered by the sample in all possible directions. One can also observe this scattering at right angle to the incident beam. The incident light has a particular frequency. If the scattered light has a frequency same as the incident light, then scattering is called Rayleigh scattering. However, it can be seen that about 1% of the total scattered intensity occurs at the frequencies different from the incident light frequency. This is called Raman scattering. Rayleigh scattering and the Raman scattering can be explained on the basis of transitions in the molecular vibrational energy levels. The molecules of the sample have a different vibrational energy levels. These levels are separated by specific energy difference. When the photon from a incident monochromatic light interacts with the molecule of the sample, the molecule may absorb the energy and rises to virtual energy state. The energy transferred to the molecule is equal to the energy of incident photon, that is, E is equal to h into nu. Here h is called Planck's constant and nu I is the frequency of incident light. The molecule then falls back to an energy level by emitting the photon. If the energy of emitted photon is equal to the energy of incident photon, then the molecule returns to its initial level. As emitted and incident photons have same energies or frequencies, then it is Rayleigh scattering and corresponding line in the scattered spectrum of a light is called Rayleigh line. However, sometimes molecules fall back to different vibrational energy levels than the initial level. In this case, the emitted and incident photons have a different energies or frequencies. This is nothing but a Raman scattering. Depending upon the final vibrational energy level of the molecule, Raman scattering can be separated into Stokes line and anti-Stokes lines. If the frequency of the scattered or emitted photon is less than the frequency of the incident photon, then it gives rise to Stokes lines in Raman spectrum. It happens when the molecule absorbs the energy, or the difference between frequency of emitted photon and incident photon is called Raman shift. In case of Stokes lines, Raman shift is negative. On the other hand, if the frequency of the scattered or emitted photon is greater than the frequency of incident photon, then it gives rise to anti-Stokes line in the Raman spectra. That means energy is released by the molecule or Raman shift is positive. Here, one thing is very important to note that Raman shift is independent on the frequency of incident light, but it depends on the nature of the molecule from which the light is scattering. Hence, the Raman spectra gives the fingerprint of the molecule since it is different for different kinds of molecules. Thus, by studying the Raman spectra, the separation between vibrational or rotational energy levels of the molecule can be determined, and hence the particular molecule can be identified. This is called the qualitative analysis of the sample. Similarly, intensity of a particular Raman line helps to determine the concentration of particular molecule in the sample. As more the number of particular molecule in the sample, more will be the Raman scattering by the molecule. This is called quantitative analysis of the sample. In order to get better insight of the Raman spectroscopy, it is necessary to understand the classical theory of the Raman effect. As we know, the polar molecules like HF or HCl have the permanent electric dipole moment because of the electronegative nature of one atom and the electropositive nature of other. Such a polar molecule can easily align themselves in the external field, shown in the figure below. But the molecules such as Cl2 or O2 do not have the permanent electric dipole moment. Still, these molecules can be polarized or orient in the direction of external electric field because of the induced dipole moment in the external electric field. This induced dipole moment is due to the shifting of electron cloud of a molecule in the external electric field. More is the induced dipole moment, more is the polarization. Among such molecules, some are more easily polarized than others by the imposition of electric field due to inherent properties in the molecule. The figure shows the induced dipole moment of chlorine molecule in the external electric field. The ratio of the induced dipole moment to the applied field is called the polarizability of the molecule. It is denoted by the symbol alpha. Therefore, the electric dipole moment is equal to alpha into E, that is the external electric field. Polarizability is an anisotropic quantity. That is, it has different values in a different directions. For example, in hydrogen molecule, for a different orientations in the external field, polarizability is different. In the following figure, for the two different orientations of hydrogen molecule with respect to the direction of electric field will have a different polarizability. Now consider a molecule in the oscillating electric field defined by E equal to E0 sine 2 pi nu t associated with the electromagnetic waves or light, where nu is the frequency of the electromagnetic wave. Since dipole moment of the molecule is depend on the electric field, therefore the dipole moment is also oscillating with frequency nu. According to the electromagnetic theory, oscillating dipole radiates the electromagnetic radiation of the same frequency with which it is oscillating. This gives rise to a Rayleigh scattering. If a molecule is vibrating or rotating with some frequency before exposing it by the electromagnetic radiation, the polarizability alpha of the molecule will also be changing with this frequency. Then the polarizability may be written as alpha equal to alpha 0 plus beta cos 2 pi nu v into t, where nu v is the frequency of vibrational or rotational motion of the molecule, and alpha 0 is the maximum polarizability of a molecule. Beta is the rate of change of polarizability of the molecule during this vibrational or rotational motion. Therefore, the electric dipole moment of the molecule now becomes E0 sine 2 pi nu t into in bracket alpha 0 plus beta cos 2 pi nu v into t, which leads to this expression. In this expression, this first term corresponds to the Rayleigh line, the second term corresponds to Stokes line. Since here the frequency is less than the frequency of the incident radiation or light, and the third term corresponds to anti-Stokes line, since here the frequency of the radiation is greater than the frequency of the incident radiation. If in this expression, if beta, that is rate of change of polarizability of the molecule, is 0, then there is no Raman scattering, or the molecule is said to be a Raman inactive. According to this classical description of the Raman effect, the amplitude or intensity of the Stokes and the anti-Stokes lines are same, but in actual practice, the intensity of anti-Stokes lines is very much less as compared to the intensity of Stokes line. Now let us see the comparison between Raman and IR spectroscopy. The Raman and IR spectroscopy are complementary techniques used for fingerprinting of the molecules. Raman spectroscopy offers significant advantages over IR and other spectroscopic techniques. Both the Raman and IR spectra arises due to changes in the vibrational modes of the molecules. However, only those vibrational modes which results in changes in the dipole moment of molecule are IR active, and those that result in a change in polarizability are Raman active. IR and Raman activities are related to symmetry of the molecule and can be expressed in terms of the rule of mutual exclusion, which states that for a molecule having a center of symmetry, the Raman active vibrations are IR inactive and IR active vibrations are Raman inactive. However, this rule is not applicable to the molecules having no center of symmetry. In such a case, vibrations may be both Raman as well as IR active. The rule is valuable in establishing the structure of a molecule such as N2 because this molecule is Raman as well as IR active. That means this molecule do not have the center of symmetry. From this, it can be concluded that the molecule has a structure NNO and not NON. These are some examples of vibrations in molecules which are responsible for the Raman spectra. As it can be seen, these are different modes of vibrations of the molecules such as symmetric stretching vibration, asymmetric stretching vibration, symmetric bending, asymmetric bending. In these vibrational modes, there is change in the polarizability from maximum to minimum. This figure depicts the rule of mutual exclusion. Now let us see the dissimilarities between the two spectroscopic techniques. Raman spectra result from scattering of light by vibrating molecules, whereas IR spectra result from light absorption by vibrating molecules. A monochromatic light beam of high intensity laser can be used in UV, visible or IR regions in Raman instruments, whereas in IR spectroscopy, the range is limited to IR frequencies. In case of Raman, scattered light is observed at right angles to the direction of incident beam, whereas in case of IR, absorption signal is measured in the same direction as the incident beam. Raman technique is a non-destructive technique. The laser sources used in the Raman technique are highly intense and these facilitate the focusing the coherent beam on a small sample area or on a exceedingly small sample volume. This is a key advantage when only limited sample quantities are available. High degree of amplification of Weak-Stokes signals is necessary in presence of intense Rayleigh light scattering. This results in higher cost of the Raman spectrometer. This higher cost may be justified against the benefits offered by the technique. That's all for this lecture. The next lecture we will see the different types of Raman spectroscopy, the instrumentation for Raman spectroscopy, and the applications in various fields of this Raman spectroscopy.